Just give. Okay. Hi, hello. First of all, I would like to welcome our audience to today's webinar. Let's wait 1 more minute and then we will start. Thank you. Okay, so let's start then. First of all, I would like to remind the audience that this event is being recorded. And second, okay, so like I said, welcome to this webinar of the HYIELD project. The HYIELD project is a European funded project, and this webinar is organized under the framework of Horizon Europe and the Clean Hydrogen Partnership. For today's event, we have several speakers. First of all, we have Álvaro, co-coordinator of the project, and who will introduce the project itself. Then we have Luis from Waste to Energy, followed by Igor from H2Sign and Axel from Minkatech Energy. These three partners are the main technological partners of the project, and they will talk a bit about their companies, their technology, and their role in the project. And finally, we have a special guest, and that's Christian. He is representing our sibling project, Karma H2, and he will give us a short description of what the project is about. Follow their presentations, we will have a round table, and we will finalize the session with a Q&A where you can ask as many questions as you want, and please raise your hand at the end for your questions. So without further ado, I guess, Álvaro, please, if you want to start with the presentation.
Thank you very much, Laia, for the organization. I'm going to share my screen, and thank to all the assistants to this webinar for coming and joining us. Okay, so HYIELD project is a project for developing a novel multi-stage steam gasification and syngas purification demonstration plant for waste to hydrogen conversion. This is a project that has been co-funded by the European Union within the Clean Hydrogen Partnership program. This project has an overall budget of 15 million euros and a grant of 10 million euros. It started in January 24 and it's going to finish in December 27. HYIELD project will deploy a robust multi-stage steam gasification and gas separation process that goes beyond the state of the art to overcome the current barriers facing the development of waste to hydrogen solutions. The solution will be demonstrated at 3 megawatt scale at a cement plant in eastern Spain, where local organic waste streams will be exploited to produce high purity hydrogen that will be subsequently used for cement production. This is a consortium that is composed of 14 companies from Spain, France, Germany, Norway, and Luxembourg. And this project has a vision is to address these challenges as waste disposal. There are territories with limited treatment options, low population density areas, islands, with limited infrastructure to manage waste, and the most common methods are landfilling and incineration. We are expected to have 3.4 billion tons by 2050, and this is a very rich resource of energy that could cover communities' energy needs. This comes with challenges for recycling and producing energy. And also we have the decarbonization challenge in hard to electrify sectors as shipping, aviation, and cement industry. So for this, we propose this gasification solution with the motivation of developing a new low-cost pathway for production of hydrogen from waste. The plant is going to be installed in Alcanar plant, which is owned by Cemex. It's located in Tarragona, Catalonia, Spain, and This is an overall view of the concept of the project. We start with the waste management, which is being studied deeply by Veolia and Setaqua. They are analyzing different kind of wastes and study the suitability of these different wastes for multi-stage gasification and gas cleaning, which main technology developer is waste to energy, and my colleague Luis will explain you more later about this technology, followed by the purification stage, which is led by H2Site, that we'll also present today, followed by metal hydrogen storage led by Menkate, that we'll also explain today. And finally, this hydrogen will be consumed in the cement factory. There are other research centers and companies supporting the development of this project. Okay, Invenia already gave us the welcome. Sintef, Synthelion, Aristen are providing support in the engineering. Okay, Eureka Digital Twin, Mactel is developing the control system, and for replicability studies, ArcelorMittal, Lafarga, and Enagas are providing support. I don't want to go into many detail because my colleague Luis from Waste to Energy will explain the process a little bit more, but just to quickly mention the core innovations of the project, which is waste feedstock characterization, control, and supply methodology for waste to hydrogen applications, process design and optimization for multi-stage steam gasification and gas cleaning. Third innovation is exploitation of waste heat from heavy industry for enhanced allothermal gasification. Innovation 4 is membrane reactors to separate 99.97% of hydrogen from syngas. The fifth is the metal hydrogen storage, and the sixth is the AI-driven digital twin for optimized design and operation and for replicability studies. So here you can have an overall view, okay, of the different compositions when going from one reactor to the other one, and when going through the different cleaning stages of this multi-stage gasification process. The methodology follows a classic structure. Okay, it starts with planning and design to validate the process design in research laboratories, and to start with the specification basic engineering for demonstration plan. We are starting from TRL 56, and CSIC is a research center that is providing testing equipment for the initial validations. Then the digital twin starts to be developed as well, along with the detailed engineering, site preparation, and licenses preparation, start to develop the procedure for feedstock management, and starting to procure all this equipment, and finally to complete the installation. And then the third stage starts with validation and an extended testing period. And finally, we will develop the techno-economic and environmental analysis, then benchmarking with other hydrogen pathways, territorial scale-up, and EU potential, where we will assess the efficiency of the demo site, and we will compare the profitability of and environmental impact of this solution against other technologies. And we will also, in this last stage, replicate through digital twin and other studies how this solution would suit into other industries, as the steel industry and the copper industry. So this is the last slide. As I said, the project started in 2023 in January, starting from TRL 7. With the lab validation, we are increasing to TRL 6. and when this project is constructed and tested in cement, in the CEMEX cement plant, it will reach TRL7. So we will have a system prototype at a relevant industrial scale. And finally, as I mentioned, other different markets will also be studied looking for increase of affordability and economic attractiveness of gasification plants and overall the decarbonization of EU power plants. So thank you very much.
Okay, thank you very much, Alvaro, for the presentation. Like I said, this was an overview of the overall project. Now we move on to Luis. So Luis, if you are ready.
Thank you, Laia. Thank you, Alvaro, for this introduction to the project. And good afternoon, everybody who is here on the webinar. I'm going to share my presentation. I'm Luis Sanchez. I'm the manager in duty of this HYIELD project within Waste to Energy. Just a few words about Waste to Energy. We are a technological company. We have developed our own biomass and waste gasification technology. We are working in this field since around 20-25 years. So it's a long way what we have been running to arrive here. You will see later on that we have already deployed this technology for different applications, but HYIELD is a brand new application for us because from the syngas that we produce in our technology, what we will produce at the end is hydrogen instead of other applications like typically thermal applications or power applications. I will divide our technology within HYIELD in three parts, three sections. This is the first part, which is the bubbling fluid bed gasifier, patented by Waste to Energy. As I said, a few years ago we have done the patents regarding the technology. This is typically a bubbling fluid bed gasifier. Bubbling fluid bed reactors, chemical reactors, thermochemical reactors. You can find that on the chemical books on Perry, on any of the chemical books that you could have you could have seen on your university or you could have on your technical libraries. But obviously what we have done is to adapt an existing technology to be able to produce syngas of a certain quality and with a certain composition. In this case of HYIELD, what we do here is to adapt the technology to produce a high hydrogen content syngas. How do we do that? Well, first, what we do is to gasify. The gasifying agent for the technology is steam and oxygen, a mixture of both, depending on the feedstock, depending on the chemical composition and the characteristics of the solid fuel. The mixture of the steam and oxygen will vary. So this will be part of the testing process, of course, that we will do with the demo plant. But anyway, we have steam, which is at the end of the day water, hydrogen and oxygen, and also oxygen feeding into the reactor, into the gasifier, in order to react with the solid fuel that it's also feed. Everything there inside the reactor is maintained at a temperature of about 600 degrees. And on that conditions of temperature, also a little bit of pressure, with the presence of certain catalyzers, we manage to produce a current of gas that we call it synthesis gas or syngas. This syngas is mainly composed by hydrogen. As you see here on the slide, 26% molar content of hydrogen is what we expect to get from most of the solid fuels that we will test. Obviously, this hydrogen content will change, will vary depending on the solid fuel, but roughly the number is about 26% molar content. Also, together with the hydrogen, we will have monoxide carbon, we will have methane, and we will have also dioxide carbon, nitrogen a little bit, and a long list of hydrocarbons, C2H4 and others. all those components, which is not hydrogen, will be converted at the end of the day to hydrogen as much as possible, and whatever it cannot be converted, it will be removed from the syngas. There are a number of chemical reactions inside the gasifier. Here we only show the most important ones. There are chemical reactions which are oxidation reactions, so reactions that will release energy, all of them, and reduction reactions, so reactions that will need energy. Both type of reactions will be compensated in order to maintain the 600 degrees Celsius inside the gasifier. So now we go to the next step of the technology, which is a second reactor, a second chemical reactor. This reactor works at a higher temperature, 1200 degrees Celsius. This reactor receives from one side, obviously, the syngas that has been produced by the first reactor. We also will feed this reactor with a char, so the unburned carbon that will be produced on the gasifying reactor, on the first reactor. And in order to increase the temperature to this 1200 degrees Celsius, we will have a plasma torch. A plasma torch coming from an electrical arc device. Okay, it's for this project is around the electrical arc is about 1 megawatt, the capacity of this electrical device, and this is enough to increase the temperature of the syngas to those 1200 degrees Celsius. Why do we want to increase this temperature? Well, sorry, before continuing, we also will inject steam into this reactor in order to increase the hydrogen content of the syngas, and also to cool down the walls of this reactor and avoid damages due to this very high temperature. The reason to increase the temperature to 1200 degrees is to increase the content of the hydrogen in the syngas. By increasing this temperature, we promote cracking several hydrocarbons. Those hydrocarbons, when cracking, they produce on one side hydrogen and on the other side carbon. This carbon will be converted in CO and CO2, and hydrogen will remain on the syngas as hydrogen, because this is the aim of this project, to produce hydrogen in order to be used in different applications. In this case, will be on the kilns of the Cemex plant in Alcanar. This is a brand new development for us. This is really R&D. Obviously, the plasma device has been provided by a company which has a long reference list on this type of technology. But to use the innovation here is to use this electric plasma torch in order to increase the temperature of the syngas and promote the formation of hydrogen. The third part of the technology is the long train to purify the syngas. We have to remove, before feeding the membranes that will be explained by my colleague Igor later on, H2 side, with the syngas, we need to remove with any type of pollutant that you can imagine from the syngas. So the syngas, apart from what you have seen, what I have told you, will have presence of acids, because the feedstock will have for sure a little percentage or little ppms of chlor, of sulfur, brom, fluor, and all these components will promote the acid formation. We will also have solids. We will have the ashes, the same ashes that you get when you burn a biomass or any type of component of waste will be found here on the syngas. So we have to remove the ashes. We have to remove the unburned carbon. The carbon that has not reacted must be removed, because this will cause big problems on the rest of the plant. We have to remove the acids, as I said, and we have to remove the ammonia. this removal, this system is done mainly as a first stage. We have a quench. A quench is a device that will cool down the temperature of the syngas. That we will pass from 1,200 degrees to about 200 degrees. So it's a let's call it a washer of water. As simple as that. Injecting water into the syngas current. What we do is managing the syngas current to reduce the temperature. Then once this syngas has those about 200 degrees Celsius, we will pass the syngas by a bag filter, quite a standard bag filter. Of course, there are certain conditions that this bag filter must have in order to properly remove the ash and the burnt carbon. And then after the bag filter, we will have a scrubber. The scrubber will be the equipment that will remove acids and ammonia and other minor pollutants from the syngas. Once the syngas leaves the scrubbers, we will have a booster. You will see it here on the right side of the slide. A booster is a low pressure compressor. We need a little bit of compressor on this syngas in order to send this syngas to the three next stages, which is an iron sponge fixed bed filter. Again, to remove acids, the acids that has not been removed by the scrubber. The efficiency on removing acids of the iron sponge is much more higher than the efficiency we have removing acids from in a scrubber, and this is why we introduce this stage in order to further remove the acids. After the iron sponge, we have a zinc oxide bed. Again, it's exactly the same function to remove pollutants, to remove specifically acids. And the last stage of the syngas purification train is an activated carbon filter, which will remove any ppm or any component that are not desired on the syngas before feeding it into the membranes of H2 side. Activated carbon filter will be always also used to remove the solids that will be transported from the iron sponge and the oxide zinc bed to the current of syngas. There will be always some part of these beds. At the end of the day, when we say beds, it's a solid material. Now the syngas is flowing by these solid material beds. You can imagine a kind of sand. And through this sand, the syngas is flowing. So there is part of this sand when it's eroded that is transported, pneumatically transported with the syngas. So the activated carbon filter mission is to stop all these components coming from the syngas. Okay, so once the syngas leaves this filter, this carbon filter, then is fed into the system that, as I said, Igor will explain related to the H2 side technology. Next slide. Well, just to finish and a little bit about us, about waste to energy and our technology. This is a list of our main references. You see that we are building plants. Well, HYIELD is quite a big plant. It's a 3 megawatt plant. 3 megawatt plant is not at all a pilot plant, not a lab plant. So you could imagine that the gasifier in the HYIELD project is a vessel with about 2 meters diameter and 6 meters high. So this is really it's not an industrial plant, yes, of course, but it's really a size that shows how that will show for sure how the technology could deliver clean hydrogen in industrial plants in the near future. No, that's what the consortium aims to prove, of course, to the industry. I'm not going to explain all these projects, of course, but in most of them, what we produce is thermal energy in the form of steam, or also electrical energy with a steam turbine or with the gas engines, using the syngas into reciprocating gas engines. I think that's all for us. Thank you for your time. And if you have any questions at the end of the presentation, we can talk.
yes, you can actually drop them if you want in the Q&A session that we have here as well. So thank you, Luis, for your presentation. And now we move on to Igor from H2Site.
Good afternoon, everyone. I hope that you can see my screen now.
Yes.
My name is Igor Egaña. I'm one of the members of the business development team of the company, and I will be presenting to you our technology for hydrogen production from syngas. First off, I'd like to say that we are highly committed to sustainability. So that's why I'm starting with a quote from a great man, Robert Mann, the first man to have walked to both poles. He said, the greatest predator of planet is the belief that someone else would save it. As I said, our shareholders, our CEO, and also the culture of the entire organization of H2Site is committed to sustainability, and the motto that we have is hydrogen made available for a sustainable future. So I'm gonna, talk to you about 3 different topics, and I will end up with a conclusion. So first off, I will start about the background of the company, where we come from, so that you understand the ambition of the company. Then I will move on to the technology, the core technology, the only product that we manufacture, and the product that we sell to end users, and also the number of applications of the very same concept that is used in this project. The very same concept can be used for many other feedstocks or solutions for the market. I will say a few words about the syngas to hydrogen solution for this project. That is, long story short, if you want to sum up, we can carry out water gaseous reaction and hydrogen separation all in one step. And as I said, I will finalize with 3 ideas that I would like to stress. First off, on the background of the company, so the company was founded in 2020 as the result of more than 10 years of research effort between Tecnalia, that is the largest private research center in Spain, and also the Technical University of Eindhoven in the Netherlands. The 2 of them worked together for something like 10 years. And so that in 2020, the company was funded with seed capital from NG. Back in 2022, we also engaged not just NG, but also Breakthrough Energy Ventures, which is the venture capital funded by Bill Gates, and also Equinor, sovereign fund from Norway. And a couple of months back, we closed Series B investment round of 36 million euro from the likes of Hy24, MassMutual, Exelgon, Suma Capital, and Agas. And all of them are definitely partners that bring not just investment into the company, but also, they help us also to get strong commercial traction in different applications and markets. So right now, we're more than 60 people working, 35 of us hold PhDs. So you can see that we are a deep tech, right? So we are something, beyond, industrial company, where we want to create value for investors in that way. In terms of value creation, we've been able to accomplish 3 different types of milestones. We've closed commercial contracts in different locations. We've done first of a kind projects on those markets and applications where we have not been able to do commercial projects yet. And we have industrialized the production of our palladium alloy membrane. That is the core of our technology. I'll come back to this point a little bit later. So as I said, back in 2020, we were at lab scale both for the size of the units that we were doing, but also for the production of our palladium alloy membranes. But we started doing first of a kind projects, for instance, in a project called H2 Sharia. That was a demo plant for hydrogen deblender to separate hydrogen from the natural gas infrastructure at distribution level. We also built an ammonia cracker later on that was put on a boat along with a fuel cell to feed the auxiliary systems of a boat. In November 2022, we integrated the production plant for the palladium alloy membranes. Since then, we've been able to produce them without the support of Tecnalia. And all the way then, as we've done such interesting projects as, for instance, Project Amogen in Birmingham. That was an ammonia cracker for a hydrogen filling station. And right now we're closing deals this year in the range of 2-digit tons of hydrogen per day for different applications. So by 2030, we want to be able to deliver units capable of producing hundreds of tons of hydrogen per day, and that is specific to the ammonia import hubs. It's a different market that is still emerging. The technology that lies behind this concept is the palladium alloy membranes. You think about the palladium alloy membranes is what you see on the left-hand side. That's what we call a palladium alloy membrane bundle. So a palladium alloy is a hollow rod that is based on a ceramic support that is porous. And I have to say this with easy words for electrical engineers like myself who don't have a very clear understanding of the chemical concepts. But porous supports meaning with small holes. But on top of that, we put a very thin coating of palladium alloy, and as a consequence, the membrane becomes dense. So the only product that permeates to the membrane is hydrogen. Nothing else permeates the membrane. And that's the beauty of the technology, is the high selectivity of hydrogen as respect to other products. So this is, for instance, to give you an idea, this is the only technology that can separate hydrogen from helium. As you know, helium is the second tiniest molecule in the periodic table. So it's that is also very challenging. So we manufacture palladium alloy membranes, but we do not sell palladium alloy membranes. We put them in pressurized vessel, like what you see in the middle picture, and we put these pressurized vessels into container solutions for customers. So we sell what you see on the right-hand side. The systems that can produce high-purity hydrogen suitable for fuel cell applications from different feedstocks, or we can also separate hydrogen gas streams. So now getting into the technology and also applications. On the right-hand side, you can see a picture of a pressurized vessel. Now forget about the colored area there inside. So think about this pressurized vessel as empty. We feed the system with a blend of hydrogen with other gas blends. You can separate hydrogen from very low hydrogen concentrations, as low as, for instance, 2 or 5%, all the way up to 98%. So if you have a gas stream that is quite pure, but it's not good enough, for instance, for hydrogen filling stations, you can separate hydrogen and you can purify that for hydrogen filling stations. We can also, and we're doing projects of this nature, we also deblending hydrogen from the natural gas infrastructure. We have a very amazing project running out right now with SNAM to demonstrate that we can separate hydrogen from the natural gas infrastructure. That is the empty vessel. But now, if you think about the vessel where you put a catalyst, we can do two things in one step. You can carry out a chemical reaction and you can separate hydrogen. And let me explain this, how it works, for instance, for ammonia cracking. So when I think about ammonia to produce hydrogen and nitrogen, by separating hydrogen from the very same place where ammonia is being cracked, we're shifting the equilibrium of the chemical reaction towards the right-hand side. And as a consequence, we are cracking ammonia at temperatures that are way milder as opposed to the traditional approach of first having a catalytic reactor and downstream a PSA to separate hydrogen. So for instance, the traditional approach cracks ammonia at temperatures between 600 and 800 degrees Celsius, whereas for ammonia cracking, we operate our systems at temperatures between 400 and 450 degrees Celsius. So it's a great amount of energy savings. And the very same principle is applied to water gas reaction. That is what we're doing in this project. So, you know, water gas reaction is the oxidation of carbon monoxide and the presence of water steam, and so that's what we do in this project. So a pressurized vessel with a particular catalyst, and so we carry out water gas reaction, and as a consequence, we release the hydrogen content that comes in the water stream, and we separate the hydrogen that comes from the water stream, but also the hydrogen that comes from within the syngas. So that's the beauty of the technology. In one step process, we do two things that increases the hydrogen yield as opposed to the sequential approach. So yeah, unfortunately, as I said, we are a deep tech. So we have a concept that right now we are protecting along with our consultancy firms for IP. So, but anyway, we are feeding the system with steam, water steam, and the syngas that comes from waste to energy, containing 37% of carbon monoxide. And out of the system, we get a great deep purity hydrogen suitable for fuel cell applications. we get 88 kilograms of hydrogen per hour, and out of that, retentate is what has not permeated through the membrane. So it contains 32% of water steam and 65% CO2, and that is used for heat recovery purposes to maybe basically to optimize the performance of the entire plant. So there are 3 highlights that I would like to make on the technical side of the project. So we virtually accomplished full carbon monoxide conversion for hydrogen production, over 97%. My understanding is that we are around 98%, which is very high hydrogen recovery factors, over 95%, to produce 2 tons of hydrogen per day. So it's it's a first of a kind project in that sense, because it's not fully commercial, but I think that it's a pretty significant size for this type of project, and we're proud to be taking part in this project. So just 3 ideas to finalize this presentation. First of all, this concept of separating hydrogen in the very same place where water gaseous reaction occurs yields an average around 12% increase hydrogen production, as opposed to the traditional approach of first having a water gaseous reaction and downstream a PSA to separate hydrogen. Then it's a system that is very, very energy efficient. So along with the first idea, it delivers the lowest levelized cost of hydrogen from syngas. That's I think that we've been able to do a pretty neat concept along with waste to energy. And this very same technology that we're using for some projects that basically is based on the same membranes with a different catalyst. We think that it's market-ready technology that is delivered by a company that is, as you can see, fully ready for industrial scale projects. And I thank you very much for your attention. I'll leave you the floor to the next speaker.
Thank you, Igor. So yes, now is Axel's turn.
Thank you, Leila. Good morning to everybody. So, as introduced by Alvaro at the beginning of the presentation, so we are part of the HYIELD project for the Innovation 5. So the storage of hydrogen within a groundbreaking solution as we store hydrogen into solid form, which is a safe, efficient, compact, modular, and affordable solution to store hydrogen. And the HYIELD project is a challenge for us, as we will demonstrate the added value of our solution to such a huge project as part of the complete value chain to be able to feed after to use the hydrogen. So first I will explain to you the metal hydrates. Some of you maybe don't know what is metal hydrate and how to store hydrogen in solid form. Then I will give you some words about our company, the market that we address, and our contribution to the HYIELD project. So starting with metal hydrate, how does it work? So hydrogen is not in our tank in gaseous form, not in liquid form, the one that maybe you know. No, our technology is based on a metallic powder that is reversible. So in our tank, there is metal powder that can absorb and release hydrogen. And the particularity is that we are able to store hydrogen at ambient temperature with a residual pressure in the tank around 10 bars. What does that mean? Is that there is an equilibrium in between the solid state and the gaseous states inside the tank, which main of the part is in solid form. And that's interesting because we will store hydrogen at a higher pressure of 10 bars, ideally 30 bars, that's fine. And by disequilibrating our tank will directly absorb the hydrogen. And to desorb hydrogen, so to use it, it's very easy. When you open the valve, you are at ambient atmospheric pressure, 1 bar, so it releases automatically. So you see here the efficiency, as we don't need to compress, so to use energy to compress the gas, we do not require also to cold at very low temperature in order to liquefy the hydrogen. So we bring to the market an efficient solution to store hydrogen. So it's a very great advantage in terms of safety. What is interesting also is to use the cold generated during the desorption. So the absorption phase creates heat. But what is interesting is that when the hydrogen releases from the tank, it creates cold. And our tank has been designed with a water circuit in order to take this cold, to co-generate with the fuel cells in order to improve the overall efficiency of a global system. And that's a huge particularity of our design. Then we have decided at the beginning of our research to not use rare earths and to use only materials under European sovereignty. And the fact is that it is completely, so 100% recyclable. So we protect our natural resources with our technology. What else? So you have here the figures on the screens. We could, the service lifetime could go up to 10,000 cycles. And what we have measured currently by tests, it's an efficiency up to 98% for 4,000 cycles. In addition to that, we have at Minkatech Energy developed a tank management system in order to monitor the state of charge of the system and to monitor the thermal management and the flow of the hydrogen. And we can absorb 1 kilo of hydrogen in less than 10 minutes. So that's important. And as all the tanks are in parallel, we are able to reload a huge quantity of hydrogen in less than 10 minutes. So that's to present to you our technology. I will go quickly on who we are. So at Minkatech Energy, we are a French company based in Belfort in the Bourgogne-Franche-Comté region. Where we stand today, we just have raised last summer funds in order to build our factory in Belfort. So we are currently, and all the team is working hard to design and specify all the machine of our plant in order to be able by the end of this year to provide a big series of our tank. Now, just to give you some figures about solid hydrogen storage with what you know certainly more, compressed or liquefied hydrogen. First, I would like to raise the volumic capacity. The solid hydrogen storage is in between liquefied hydrogen and compressed hydrogen at 700 bars. So to store 1 kilo of hydrogen, you need 14 liters in liquefied, 18 liters in solid form, so with our technology, compared to 24 liters when you compress the gas. So when you see the cost of for many applications, you need to reduce the space of the storage. So with the solid storage, you improve the volumic capacity needed. Now, in terms of market, because all the other figures are already give that to you, as we do not need compressor, it's provide 20% of efficiency saving, and also through the fact that we do not have cogeneration, it's around also 20% of efficiency savings. In terms of market, we address not all the market, but mobility sector for all off-road machine, the railway and sea and river mobility. Also light vehicles, so what you see on the left of your screen. Now we are here today with the HYIELD project to talk about the stationary applications. So we participate with our technology to the decarbonization of industry. So what and the topic we address today. But we also can address the high capacity storage for the renewable energy, and also some application for home like boilers. Now for the HYIELD projects. So our contribution is small. We provide 10 kilo of hydrogen storage. It's small, yes, but it's an innovation, and it will help us and all the community to see all the benefits of solid hydrogen storage in terms of safety, reduction of land cost, reduction of H2 cost, operational costs, which will be reduced thanks to the hydrogen storage, the improvement of all the hydrogen value chain efficiency, and the fact that we bring a solution which is very good for the environment. No noise pollution, 100% recyclable, and no rare-earths. So I will be happy to answer your question on metal hydride if you don't know this technology, and if you need more explanations. So thank you to all.
Thank you, Excel, for the presentation. Like I said, we have this Q&A session at the end, and you can drop your questions in the Q&A button. And now we move on to Karma H2 with Christian, our sibling project. Please, Christian, go ahead.
Very good, thank you very much. So while I'm putting the slides up, I want to start to thank you for the invitation. See there. And I've also really enjoyed listening to the talks so far. I've not kind of dived into this HYIELD project and the technology that you are doing, and I really enjoyed